This is for AP Chem, and this is going to be your second lecture on essentially the language of chemistry, which is writing formulas and then going backwards and naming compounds. So we're starting on page 2 of your notes that says formula writing and bonding. And so we're going to still be concentrating on formula writing and naming. So on page 2, we're going to go down actually to the bottom of the page to start. And we're going to look at what's called an alternative method for compounds that are two nonmetals. Okay, so that's the very bottom of page 2. Now, this is a method that... hold on. Whoops, sorry guys. Oh, shoot. Let's get back to that. There we go. This method is a very conventional method. It's sort of like, an old-time method that people have a hard time letting go. Because the box above it where it talks about using Roman numerals and naming by the oxidation state was supposed to be the way, it's called the stock system. And we're going to get to that next. That was supposed to be the way that we were supposed to name things going forward into the new dawn and the new age. But people have a hard time letting go of things. A lot of people know what carbon monoxide is, what carbon dioxide is. It's very difficult. They even go back to Latin names of nitrous and nitric instead of prefixes. So it's kind of difficult to really do this thing where you just flip a switch and start naming something in a different way or mode when you have people out there trained in one fashion and now you're trying to move to another fashion. Okay, so I want to talk about this a little bit on this alternative to the crisscross method. I want to make this very clear. This is to be used for two nonmetals. Okay, nonmetals. So you now have to get in this habit of always asking yourself when you write a formula, what is making the compound? Okay, so you always question what makes the compound. Okay, if the answer is, and this is where you need to know your periodic table, and you need to know what is a metal, what is a nonmetal. If the answer is two nonmetals, you can use prefixes. So hopefully you're picking up that this is a binary thing. Okay, so this method isn't going to be something you use with a polyatomic ion because it's not a way you would name an ionic compound. You only name molecular compounds. Okay, molecular, which is two nonmetals. These are also called covalent, which we're going to get to in our next lecture. So if there is a metal, you would not use this. You never use prefix for a metal. Not in our scope of our class. Okay, I just need to make that clear because when you go on in chemistry, you learn about lots of different types of compounds that can be made. We're talking basic building block, baby steps. Let's start with a simple. So we're going to say you never use a prefix for a metal in the compounds we deal with. If you see a metal, it is ionic. You name the metal, you name what comes next. Okay, you do crisscross to get the formula. But if you see two nonmetals, you can use a prefix. Now here's the big key. Prefix uses absolutely no crisscross. So that's a change in gears. Okay, we were crisscrossing. Now I'm telling you, whoa, if you want to use prefixes, you don't crisscross because you're not dealing with necessarily charges. You're dealing with shared things and you name them differently. So there's an example written there, and we're going to do some more on a whiteboard, and then we'll go back and talk about the rest of the page. And actually, we're even going to go on and talk about the next page. Okay, so as we do this, and we look at what's there. I have phosphorus and I have oxygen because the ox, that's the root. So that's 2 nonmetals. Because it's 2 nonmetals, we have prefixes in the name, the di and the pent. Okay, so now you have to start to learn numeric prefixes. There really isn't a cheat for this other than knowing it. And so, things like mon is 1. I have to be careful not to touch the buttons on my pen. Di is 2. Tri. Think about math. Triangle. Tetrahedron. Pentagon. Hexagon. Septagon. Actually, it's heptagon. Sorry. It's a late night for me. Octagon. Nine and deca. Or deca. Yeah, deca. It's 10. Okay. That'll get you through most prefixes. If you're given a name, you look at the prefix. That prefix is the subscript. I don't crisscross. I write phosphorus, I write 2. I write oxygen, I write 5. So let's do a few. So if I have, let's do nice color. That's, come in. Come in. Okay. Nitrogen, dioxide. Now notice, no prefix in front of the first means that the subscript is 1. You don't use mono on the first name. We don't say monocarbon dioxide or monocarbon monoxide. Now, sometimes the mono and the gets shortened to mon, like deca might get shortened. It just depends on the flow of it. Okay, so nitrogen, we just write. Dioxide, oxygen, di, 2. Dinitrogen. Oh, I'm just making this up. Octo oxide. Okay, the oct is 8. Oxygen, so O8. Nitrogen, N. Di is 2. Notice we leave it. Don't simplify. If this was a metal, you'd simplify. I'm going to give you that's a 7. It's not a 1. It's a 7. Let's say this is a compound. I'd look at this to name and I'd say, oh, this is tri, because it's 3. Phosphorus. 7. Heptasulfide. Right, sulf is the root. Take off the ending of add IDE. That's how I name. It's a binary, it ends in IDE. I'll make up another one. Try to make up another one. Tetracarbon. Oops, carbon. Penta, because of 5. Oxide. Again, the ox goes for the oxygen. The penta goes for the 5. The tetra is the 4. And then the first one is carbon. If I had CO2, you might be tempted to put monocarbon, but it isn't. Remember, if it is carbon, if it is a subscript of 1 on the first element in the formula, you just need the name of the element. And then it's dioxide. Okay. Now, this little baby here can be named a couple different ways. We can use prefixes or we can use oxidation numbers. If you use oxidation numbers, so I'm going to erase the canvas because I'm getting low and it's hard for me to write really low on the canvas. Okay, so if I did this one, we said that that's carbon dioxide. Okay, now, if I were to do charges, we say by default oxygen has a 2 minus. Right, so right now I have 2 times a 2 minus plus something for the carbon has to add up to 0. So carbon, this will be a minus 4, adds to 0. When we rearrange, carbon's a plus 4. So we can also name this by this thing called oxidation number. This is carbon 4 oxide. Now when you use a Roman numeral, okay, then you have no prefixes. And this is called the stock system. The hard part is determining this Roman numeral, and the Roman numeral refers to the charge on the element named before the Roman numeral. Right, so if I had the same thing, well, if I did this, N2O4, okay, first I'd have to say, okay, what's the charge on nitrogen? Well, you kind of do the same kind of thing. I've got 2 nitrogens plus 4 oxygens, and they have to add up to 0 because it's a compound. 2 N's plus 4 times a minus 2 will give me 0. 2 N's give me a positive 8. Each N has a plus 4. I'll show you a cheat method. Okay, so this would be nitrogen 4 oxide. Cheat method. Reverse crisscross. Throw that one up there. Throw this one up here. I'd have N plus 4 O 2 minus. Then you ask on this guy, is this normal? Would that be the usual charge for oxygen? The answer is yes, because oxygen is usually 2 minus. So now I know that this is correct, and I wouldn't have to go through the math. Okay, let me clear this off. Now we're going to look at the little box above it. So I'm just going to move this down a little. Okay, this is called the stock system, or Roman numeral. Okay. This can be used for 2 nonmetals, although by convention, as I'm going to tell you, you will see prefixes more than this. But mostly with transition metals. Now, because why? They can have more than one oxidation state. Because of those d electrons, they can do different things with their electrons. They can move them around more. They have more space. They have, all these different shapes to put them in. So you can lose more and you can move them more. So first you have to realize that the Roman numeral is the charge on the element before the Roman numeral. So if we look at the examples here, and they're already done out, this says iron 2 oxide. So if I were to write the formula, I would use Fe for iron, but it's a positive 2 because the number in the numeral is 2, as opposed to this one. The number in the numeral is 3. So this one's a plus 2 state, charge state, oxidation number state for iron, where it's iron 2. And if you're iron 3, it's a 3 plus. It's a lot to keep straight, like this is like, look, if any of you are taking a foreign language, whether it's Spanish or French, you're getting clobbered with vocabulary. Okay, and it's something they found out that they were very weak on in the past. My son would attest to it because he took the Spanish SAT and said, I didn't know half the words. So he didn't do very well. So, what I'll say to you is, you have to practice just like you would a foreign language. So you have to know and be able to recognize what this Roman numeral means and how to use it. So when I write the charges up there, oh look, these charges add to 0. I can just write it like it is below. These do not add to 0, so I crisscross. Notice the difference in the formula. This is what we call the, oh God, my brain just went blank. Multiple ratio, law of multiple proportion, because iron under certain conditions will combine with one oxygen, but iron under other conditions will have a different charge state and combine with more oxygens. So this is a law of multiple proportions. Now, this gave you the formula, like the name, and you wrote the formula. If you looked next to this copper-containing one, you have the formula, and you've got to write the name. And when you go and you say, is this a transition metal? And the answer is yes. Then you might say, oh crap, I have to figure out charge. Now, remember, there's certain transition metals. Actually, I'm going to go to this pen because it's not supposed to be pencil, it's supposed to be a pen. Right? Certain transition metals. Nickel will be 2+. Zinc will be 2+. Silver will be positive. So technically, you don't have to use the parentheses. Zinc, you will not use the parentheses. If you say zinc 2 chloride, people will look at you like, why are you saying that? Because zinc can only be a 2+. Okay, nickel's usually a 2+, silver's always 2+. We don't say silver 1 chloride, we just say silver chloride. Okay? So these guys, you kind of have to know that's going to be their charge. When we go back to looking at our diagram over here, or our formula over here, if you do a reverse crisscross, that's what this was a reverse crisscross, you would get a -1 for sulfate. And you have to know your charges. Sulfate is not a -1. So that's wrong. That's why there's an X through this. So since that's wrong, I have to go back and do algebra. Sulfate's a 2-. I have 1 copper. So if I move that charge over, copper has to be a +2, and I would name it copper 2 sulfate. Here's bismuth. Now, could I use bismuth? Bismuth's kind of like the tricky one. Bismuth might be a metal where they might use a prefix because of where it's located in the table. Because it's part of the right, But technically they shouldn't use prefixes, so you're supposed to figure out the charge. And again, you can do a reverse crisscross and go, oh yeah, this is right. I don't have to do algebra because the charge on oxygen is correct. I'm going to go with that, and it becomes bismuth 5 oxide. Okay? Need to know those Roman numerals. The other thing that's on this page is, how do you go backwards? If you're given a formula, how do you name it? So I'm going to do a little flow chart, and I'm going to do this as I go along, so you're going to be I mean, we might come up with a better version of it. You can get out a piece of paper and use it and do this flow chart. Let's see if I can do this on here and if I have enough room. Okay, first you're going to start and say, as a question, are there more than 2 symbols from the periodic table? So if the answer is no, then you're going to ask, then this becomes binary. Okay. If the answer here is, and I'm not talking subscripts, simple symbols. The answer here is yes. Oops. I'm going to go put this beside the little thing here. If it's yes, then we're going to say polyatomic. Now we're going to focus on binary for a second. Then we're going to ask the question, so the next question we're going to ask is it 2 nonmetals? So if the answer is yes, we can use prefixes. Okay. If the answer is no, right, we have to ask, next question, is there a transition metal? So if the answer is yes, you have to determine the charge in the metal. That's first thing. Write the name of the metal. Put charge in parentheses, Roman numeral, and then write the root of second element, and then end in IDE. CuCl2. It is binary. So you go through and you say, are there 2 nonmetals? No. So is there a transition metal? Yes. Okay, so if it's a transition metal, I have to go, oh, what's the charge on that? Reverse crisscross. My reverse crisscross, this is a 2 plus, and this is a minus. That's normal. This is good. So this would be copper 2. I'm going to squeeze it over here. Chloride. Okay, going down the other one. Is there a transition metal? No. Okay, so then it becomes easier. Write the name of the metal. Write the root. Whoops, root. Not route, root. Of second element. And then end it in IDE. If we have prefixes, right, you're just going to use the appropriate prefix and name first one. Use prefix, root of second, and end in IDE. Notice these all end in IDE. Binary ends in IDE. Okay. Now, polyatomic. Does it start with a metal? Oh, I'm getting over to my controls, that's why. I can't make the T, guys, because it's too close to my controls. So if the answer is yes, you're going to split after the metal. Find the second part on your ion chart. And then you have to name it. So you name the metal. And then you write the name of polyatomic ion. Now you got to be careful if it is, and I forgot to put this in here, if metal is transition, you need to determine its charge. Just like we did for binary. Right? If it's a no, okay, you have to look at the positive ion. It is most likely ammonium, most likely. It could be other ones. They have what's called mercury 1, which is dimercury. That's the only other real positive ion that you'll see. Okay, so you name the ion, whichever one it is, ammonium or mercury 1, and then look at second part. If it's an element, you'll do the root plus IDE. If polyatomic ion, you write the name of the ion. That's a rough flow chart to try to get you through naming. Okay, you can always pause the video if you're trying to keep up to write down your flow chart. Okay, I'm going to go on, but you can pause it when you're ready. You can hit play to play on further to get more of the notes. Okay, so we're going to go on to the next page. This is patterning off of your ion chart. If you look at the ion chart, you'll start noticing the thing that I talked about in writing an ionic formula thing. We have the most common state of an ion. Should be moving. Okay, chlorate, borate, iodate, they're all halogens, so they all follow the element O3 minus, right? Bromate, iodate, they all follow that. If I lose an O, goes off, this becomes bromite, iodite, ITE, ITE. If I lose another one, I go hypo, meaning going too low, so I'd be hypobromate, hypoiodate. Okay, following that pattern. If I go the other way and I gain an O, then it's perbromate, periodate, per. Again, Sulfur follows that. Sulfate, sulfite, but you don't get the pers and the hypos. Nitrate, nitrite. Phosphate. Phosphate is PO4. Right? So sulfate is SO4, 2 minus. PO4, 3 minus is phosphate. Nitrate, NO3, minus. Look, minus 1, minus 2, minus 3. Those are your big ion pairs. Can lose an O, go to an ite. You also have these things called bicarbonates, bisulfates. That's a hydrogen sulfate. So if this you have HSO4 minus, that's the same thing as bisulfate. If you have hydrogen carbonate, it is the same thing as bicarbonate. All right, so that's like baking soda. So this is the counter ion in sodium bicarbonate. What they give you when you have an upset tummy, right? Sodium bicarbonate. That's not bright enough. That's awful. What happened to my really bright? Oh, I guess it's that one. NaHCO3. Right, this is baking soda. Goodness. Yeah, those. That's better. Baking soda. Oh, I know why. Silly me, I was using a pencil instead of the pen. Okay, so with baking soda, that is what you use to make cookies. Okay, this part gives a base when added to water. So if you drink a, and it's salty as all heck, tastes funny, it's got a slimy feel to it, because bases have a slimy feel. You make a solution of that and you drink it, and it'll settle a stomach that's very acidic. Because so if you had too much tomato sauce and your stomach hurts, you drink the baking soda and then it reduces it. Gets rid of, it neutralizes it. Okay, so keep that in mind. Patterns, 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 patterns. Naming an acid. 2 different types of acid. A binary acid. So binary means, and I'm going to move this up. Well, yeah, I'm going to move this up. Okay, so, oh, it didn't pick it right. Goodness. Hold on a minute. It's supposed to be doing a full screen snip, my little friends. That means what's on the screen. There we go. So binary means you've got 2 symbols. One of them is going to be H when it's an acid. Okay, so this is one of the symbols followed by something else. Binary always starts with hydro. So if you ever see hydrochloric, hydrofluoric, hydrobromic, hydrosulfuric. Okay, notice when it comes to acids, they keep the whole sulfur in there. They don't go sulfic. They keep the whole sulfur in there. That, starting with hydro, tells you it's just H and the symbol of the element, and then you do a crisscross. If you see binary, when you go backwards, it has to start with hydro, and then you do the symbol ic acid. On the bottom, ternary is a way to say more than 2, so they're polyatomic ions, still starting with H though, because that's a signal that you have an acid, other than the very special one, which I'll talk about in a second. So it's H followed by the polyatomic ion. Now this is where you need to know your ions. Right? You have to know ClO3 is chlorate. There's a convention. You take the 8, take that ending off, change it to ic, call it acid. Notice, no hydro. You take the name of the ion, get rid of the ending, put ic on it, and say acid. That means it's one with the higher amount of O's. If I look at this one over here, it's nitrite to start, and it goes to us. Lower amount of O goes to us, higher amount of O goes to ic. So sulfuric acid is SO4 2 minus. Sulfurous is SO3 2 minus. And then you have to do crisscross to get your formula. Don't forget, everything has to add up to 0. H is always a positive when it's the positive, a positive 1, I should say, when it's the positive in the formula. On the bottom, we have a special little group here. We call it the COO group, COOH. This is a biological acid. This is what you don't get taught anymore, which you should get taught when you're in AP prep for bio. Anything that ends in COH is called a COO. This is actually the H that's responsible for coming off. Amino acids are this way. They have a COO group on them. That's what building parts of proteins. Okay, so this is a quick naming of the acids. You really should be able to write and name an acid at any point. We will focus more, too, when we go back and do specifically acid-base chemistry. I'll refresh, do you remember how to name an acid? How we write its name, how we know its formula from its name, because we just build on that. Okay, let's see. I just want to check to see if there's anything else. That's it for naming, and that we'll practice, and then we're going to go on to bond and bond traits.